So welcome to lecture 13 of power system protection course. So in the previous lecture, that is in lecture number 12, we discussed about the directional overcurrent relay, different types of connections, how we can connect the directional overcurrent relay. Then we have seen the implementation of directional overcurrent relay in a three-phase distribution feeder, and also we have shown how it can be implemented in a mesh network, and also we discussed about the algorithm used for the implementing or for the setting, for giving the setting in a directional overcurrent relay in a mesh network. Already we talked about these things, and that actually covers your directional overcurrent relay. In fact, it covers the overcurrent relay. And in this lecture we'll discuss about the distance protection. What is distance protection and why it is important? All these things we'll talk. Then we'll talk about different types of distance protection, how it can be implemented in a using the electromechanical relay and also numerical relay. We'll talk about this. So let us start with so let us first see what are the drawbacks of overcurrent relay. In fact, there are certain drawbacks of overcurrent relay, because overcurrent, as I mentioned, overcurrent relay is used only in the distribution feeders or distribution network, not in the transmission line. Why it is not being used in the transmission line? Because it has certain drawbacks. Let us see the drawbacks. So let us consider a line, a feeder, let us say. Okay, so for this feeder, we can say it's a radial feeder, and for this the source is E, and your source impedance is ZS, and it has two buses, right? And also bus B is connected further. Okay, now we can see here that we have a relay here at bus A, okay, and with a pickup current of IPU, right? And now suppose the fault happens here at point B, at bus number B exactly, then what happens? And or the fault happens at B1, what happens? At B2, what happens? Let us see it. So in fact, if we'll plot the characteristic of fault current versus different type of fault current versus distance for different types of fault, we can see here the plot has been done for fault current versus distance for three-phase fault, for LLG fault, for LG fault, right? So now you can see here, when the distance is 0 from the relay location, from bus A, obviously the fault current will be the highest for three-phase, whether it is three-phase fault or LLG fault or LG fault, right? For three-phase fault it is E by ZS. For LLG fault it will be little different. For LG fault it will be different. Okay. Now if the distance of the fault location will change, right? So suppose the fault happens at B1, obviously the magnitude of the fault current will decrease for each of the different type of faults, right? For B1, B2, B and B2, right? So now if we'll see, if we'll put the pickup current IPU, right? So for that, the reach for the LG fault is fine, right? Okay, reach for LG fault will be B1. Okay, now beyond this it will not pick up for LG fault, up to B1 only. So therefore it is called the reach of the relay. So reach of the relay up for the LG fault will be up to B1, right? So that means after B1 it will not pick up. If we set the pickup current at IPU, right? Let us say this is IPU, right? Now similarly for this pickup current, the reach for the LLG fault is up to B, right? Up to point B. Beyond point B it will not pick up. That means your relay will not operate. Okay. Similarly for three-phase fault, the reach is up to point B2. Okay. The reach of the relay will be point B2. Beyond B2 it will not operate. That means for different types of fault, the reach of the relay varies, right? We can see here that the three-phase fault is having the highest reach, right? Here we can see this is the highest reach for the three-phase fault, right? Up to this point B2. Then next higher reach for the relay is for LLG fault, and the lowest reach is for the LG fault. Obviously for the LG fault the magnitude of the current is very less as compared to LLG and three-phase fault. Therefore we can say ILG is less, ILLG is less than I three-phase fault. Okay, so that means I three-phase means I can say ILLG. Okay, so this is the range of the magnitudes. So now we can see very well when the fault type, with the variation of fault type, your reach of the relay is varying, right? Similarly, obviously it is a variable thing that we don't know which kind of fault is going to happen in the network, right? So that is how the variation in fault type will cause the reach of the relay to vary, right? We can see here the reach of the relay for LG fault is up to B1, for LLG fault is up to B, for three-phase fault up to B2, right? Now let us see another kind of variation. If your source impedance varies, that means your obviously because the source impedance never remains constant, the source impedance depends upon the configuration of the network, right? Configuration of the network. So as the configuration changes, so your ZS will vary, and therefore the fault current also varies, and therefore the reach of the relay also varies. We can see here, if we consider ZS3, which is the highest value of source impedance, right, taken here. So ZS3, if we'll take in this sequence, suppose ZS1 is less than ZS2 less than ZS3, then for ZS3, which is the highest value of source impedance, obviously the reach will be the lowest, that is up to B1, right? Similarly, for the next higher value of ZS, that is the source impedance, the reach will be B, the reach of the relay will be B for that particular pickup current, that is I per unit, I pickup, right? Similarly, for the lowest value of ZS, that is ZS1, right? For ZS1 the reach will be the maximum, that is up to B2. Beyond B2 the relay cannot operate, right? So therefore we can see here that the reach of the relay depends upon various types of fault, and also because the fault is varying in nature in the network, we don't know which kind of fault may happen, and therefore the reach also varies, reach of the relay, and therefore the relay maloperates. And similarly it also depends upon the variation in the ZS, that is the source impedance. So now we can see that this overcurrent relay there is a chance that it will maloperate when there is a variation in the fault type and the variation in the source impedance. Now this, with this kind of consideration, it is not suitable to use this overcurrent relay in transmission network. So it is not suitable. It is not suitable. Why it is not suitable? Suitable to use in transmission network. Okay. Why it is not suitable in using in transmission network, but somehow it is suitable. It is suitable to use in distribution network, because in distribution network we know that there is no issue of stability, because in the distribution network has no issue of stability, because this is mostly passive network. Nowadays it is becoming active, and it is not interconnected, it is radial feeder, and sometime if the relay maloperates, even less interruption happens, and then it is fixed and the supply is reinstalled. So therefore it is not an issue in the distribution network. But in case of transmission network, so there is always issue of stability, right? So there is a issue of stability issue. So this stability issue really, it sometimes causes the whole system blackout, because some maloperation happens in distribution network is okay, that for a particular area it happens, right? So it will make blackout for a particular small area. But if some maloperation happens in the transmission network, it causes the stability issue in the whole transmission system. In fact, the transmission network is the backbone of the system, right? Of the power system. And something happens and it in fact causes the cascading effect. Because of that, there is a chance of blackout in the system. Okay. So in order to avoid this blackout, it is not advisable to use this overcurrent relay. So therefore it is not advisable to use this overcurrent relay in transmission network, right? So therefore it is not advisable. So then what we should do? How we'll protect our transmission network? Let us see this. So therefore this distance protection came into picture. Why it is called distance protection? We'll talk about this. And what is the cause that it is called distance protection? Let us see. Suppose a transmission line is here with a source E and source impedance ZS, and with the same kind as we have seen previously, right? And let us say there is a relay which is connected with CT and PT. Through CT we are feeding the current, and through PT we are feeding the voltage VR, right? Now what happens if I will say this ZL1, suppose the fault happens at F1 at this point, then the impedance seen by this relay will be ZL1, right? Okay, so that is nothing but VR by IR. Very simple, right? Similarly, if the fault happens here at point B, the impedance seen by this will be ZL2 will be also VR by IR, right? That is, if we know the voltage measured at relay point and the current measured at the relay point, then we can find easily the impedance, right? So that means this is ZL2. Okay, this is ZL2. Sorry, this is ZL2, and this is your ZL1. Okay, and this is ZL1 is ZL3 will be equal to again VR by IR when the fault is at point F3. Okay, let us say this is B1, this is B2. Okay, so now we can see this is your you can see this is your in fact this is your equivalent equivalent network of the transmission line, where we can see this is your VR measured at the bus A, and the current passing through the network is IR, which is being fed to the relay. So that means if we feed VR and IR both to the relay, then obviously we can find the impedance up to the fault point, right? Up to the fault point we can find the impedance. So now what is the what we can see here, that for different types of fault, right? For different types of fault, for F3, which is external to the reach point, that is a point up to bus number B, right? So for F3, the current at relay location IR, that is IR3, let us say, okay, that is IR3, let us say, and the voltage at relay location, let us say that time is VR3. Then if we'll compare the voltage measured at relay point VR, that should be greater than IR3 Z set. So that way it will restrain. If the reach of the relay is, if your set point is up to bus number B, up to this point, suppose Z set is equal to up to bus number B, that means your ZL2 is equal to Z set, then obviously this is your reach point. So for the external fault, for this fault, what will happen? It will not trip, because your VR3 will become greater than IR3 Z set. You can see here, right? So that will be IR3 Z set. Okay. So therefore the relay will restrain. And for F2, for fault at F2 at bus B, which is the reach point, right? So your relay current, let us say IR2, and voltage at relay point is VR2, and as per the rule, so it is the verge of operation, so therefore we can say that VR2 is equal to IR2 Z set. That is the verge of operation. Similarly, for fault at F1, which is internal fault in the reach point, up to the reach point, right? So at that time, if the current is IR1 and voltage is VR1, then I can say the VR1 is less than IR1 Z set. Obviously, right? So therefore the relay will trip. Okay. Now from this above table, from this table, what will be the trip law? So your trip law will be, if your VR, that is the voltage seen by the relay, should be less than IR Z set. Okay. So that is IR is your current seen by the relay, and Z set is your set impedance in the relay, right? Z set is your setting value, setting of the relay. Okay. Or else it will restrain. Okay. So now if your VR by, then I can, from this equation I will find if VR by IR is less than Z set, which is the setting of the relay, then it will trip, or else it will restrain. Then from this I will say that if ZR is less than Z set, then it will trip or else restrain. ZR is your that is impedance seen by the relay. Impedance seen by the relay. Okay. And your Z set is your setting value of the relay. Okay. So now if we'll plot the characteristic, that is relay voltage versus relay current, that will be a straight line, okay, obviously passing through origin. Now if we'll take the slope of this will be the Z set, okay, and below this curve will be the trip region, and above this region is the restraining region. That means the slope greater than this, that means if I'll plot a line here at this point, right, so that means for this line whatever slope I will get, that is your ZR. Okay, so here ZR is greater than Z set. Okay, and if I'll plot a line here, for this your slope is, this is your slope of the line. So here the slope is ZR, which is less than Z set. Okay, so now therefore this region will be your trip region and this region will be your restraining region, right? Okay, so this is when we plot between the VR and current IR. Okay, now let us plot the Z, that is the impedance seen by the relay in the Rx plane, that is we call impedance plane. So R in the y-axis and X in the R in the y-axis and X in the x-axis. Okay, sorry, R is in the x-axis and your reactance is on the y-axis. Okay, so now let us see this, how it will look like. Okay, so here the same diagram, same feeder is taken, that is having the bus A and B here, and the source value is E and source impedance is ZS, and the setting of the relay is Z set. Okay, and different for different fault, the impedance seen by the relay are here. For fault F1, the impedance seen by the relay is ZL1. For fault F2, it is ZL2. For fault F3 is ZL3. And the reach of your relay is up to point B, up to bus number B. And when the fault F3 happens, it is external fault. And when F1 happens, it is internal. It is considered as internal fault because it is within the reach. Okay. So now let us plot these different Z's in the Rx plane, that is R in the x-axis and X in the y-axis, that is X is the reactance here, right? So that means the R is real of V by I and X is imaginary of V by I. So let us plot. So here for F1, it will obviously lie, if we'll set, this is your set value, right? If we'll plot the impedance here using this Rx plane and considering the setting Z set value, Z set, if we'll plot, it will be a circle, right? And it will, so wherever we have, it is Z set, right? This is your Z set. This is also Z set. So Z set. Now for fault F1, if we'll mark the point, then obviously it will be here, right? It will be within this circle. And for F3, if we'll mark the point, obviously it will be outside the this region, right? That is in the restraining region, right? And this is your fault characteristic. And if we'll mark the F2, it will be exactly on the circle, on the circumference of the circle, where the line, the fault characteristic is crossing the circle, right? So that is at the verge point where the relay starts, or verge of operation. Okay, when the relay starts its operation. So this is the operating characteristic of the relay, that is we are plotting the Z set, right? This circle is your operating characteristic of the relay, and this straight line is known as the fault characteristic of the line, fault characteristic line. Okay, and the line which is making an angle of theta L with respect to R is nothing but tan inverse omega L by R, right? So that is, so L is your inductance of the line, inductance of line per unit, in per unit or whatever you can take. R is in per unit, R is resistance of the line in per unit. Okay, so therefore L and R are taken from the line parameters, and it can be plotted. This fault characteristic also can be plotted by finding the theta L. Okay, now this is your simple impedance relay, we can say, right? When so this characteristic is uh, for when the fault is, this fault characteristic is for when the fault is a metallic fault. Metallic fault means there is no arcing, it is directly sorted to the ground, right? Metallic. But in practice, most of the time we found that the faults are arcing faults. So therefore let us consider the arcing fault, how the fault characteristic will look like. So if we'll consider the arcing fault, so how your impedance will look like. So your impedance, obviously this is your Z set, right? This is your Z set, okay? And if we'll add the arcing resistance, suppose we have a arcing here, okay, and having a resistance of R arc, okay, so that will R arc, sorry, R arc, right? So that arcing resistance, if we'll add to the impedance, okay, so that will in fact give us fault characteristic to us. Now your fault characteristic for different fault at different fault point, it will be like this, okay? And for your setting value, up to the setting value, the fault characteristic will look like this, okay? And obviously it will make an angle of theta L, this line, and this line also will make an angle of theta L, okay? They are parallel lines, right? So this is your fault characteristic will change because your R arc, that is the resistance due to the arcing, will be added to the impedance, right? Other thing will remain same, the operating characteristic will be remain same because it is based on the, this operating characteristic is based on the Z set, okay? So therefore this will remain same, only your fault characteristic because of the arc resistance will change, it will be having two parallel lines, it will like your trapezoid, right? Okay, and because of that, sometime whatever your reach is, so at the reach point your relay maloperates because of the arcing resistance, right? You can see here up to here the set point is Z set up to point B, right, bus number B, but somehow if your arcing resistance is added, now your fault point or your Z, actual Z is lying outside the circle, that is in the restraining region, right? Restraining region. So therefore sometime because of this arc resistance, your reach value or your reach point will decrease. Now we can see here your reach point will come to here. So your reach point will reduce. The relay reach point will reduce. Now it is reduced by this, right? We'll talk about this more in detail for different types of relays. Okay. Now let us consider simple impedance relay. Okay. So already we talked about it. Now we'll talk about more by deriving equations and implementing it. So now let us write the trip law for a simple impedance relay using the universal torque equation. What is universal torque equation? Now this is your universal torque equation. Why it is called universal torque equation? Because it involves the different it involves the different torque components which are produced because of the different elements, which is possible in implementation, right? Now you can see here the first component, which is showing the component of torque, which is because of the current, that is current seen by the relay. And the second element we can see here, it is because of the voltage seen by the relay, that is marked as K2 VR square. First one marked as K1 IR square, and second one is marked as K2 VR square. Similarly, the third component is because of the, this is also a torque component, it is because of the directional element. So this is because of the current component, current seen by the relay, and this is because of the voltage seen by the relay, this is because of the directional element, okay, both voltage and current, okay. directional element. Okay, and sorry, this is in fact whole is your direction because of the directional element. Now your K4 is your, it is because of the spring, the torque, that is opposing torque, it is because of the spring. Okay, because of the spring, right? So now this, therefore it is called the universal torque equation, because it contains all the components, all the possible components of the torque development in a relay, right? How the torque is. So T is your net torque on the actuating structure of the relay, and K1 I square is, IR square is the torque due to the current fed to the relay current coil, and K2 VR square is the torque due to voltage applied to the relay pressure coil, and K3 VR IR cos theta minus tau is the torque due to the directional unit or directional element. Theta is the angle between voltage and current fed to the relay, and tau, we know already this in the directional overcurrent relay, right? Tau is the maximum torque angle for the directional unit. K4 is the torque due to spring, which can be neglected compared to the operating torque. Okay, this can be neglected when the relay is on the verge of operation. So when the relay will be in the verge of operation, when this component will be equal to 0, at that point the relay will be in the verge of operation and K4 can be neglected, right? Now let us consider that K1 is positive and K2 is negative, and let us assume that K3 is equal to 0. Now let us see what will happen to your universal relay equation. Therefore the relay will trip when, from your relay universal relay equation, what you will see, your universal torque equation for relay is this, right? So here we are assuming K1 as positive, K2 as negative, and K3 as 0, and K4 is neglected. So now what will happen if your relay wants to be, if your relay is to be operated, then obviously your K1 IR square should be greater than K2 VR square. At that point is only the relay will operate. That means at the verge of relay operation, your K1 IR square will be equal to K2 VR square. So this is at the verge of operation. But when the relay will trip, this will be your K1 IR square will be greater than K2 VR square, right? Now your K2 VR square will be less than K1 IR square, right? Okay, just by inversing, right? So now from this equation we will find that VR square by IR square, from this we will find VR square by IR square should less than K1 by K2, and VR by IR should be less than K1 by K2 under root. Okay, and VR by IR will be equal to Z seen, that is the impedance seen by the relay. So this is nothing but the impedance seen by the relay, okay. So therefore this is your Z seen. Now your Z seen should be less than K1 by K2. So that means if your Z seen is less than Z set, then it trip, otherwise it will restrain. That means your K1 by K2 under root is your Z set. Okay, so we can therefore describe the simple impedance relay as an overcurrent relay. So this is nothing but a simple overcurrent relay with voltage restraint. That means your voltage coil is restraining and your current coil is giving a forward torque, and your voltage coil is giving a restraining torque. That means voltage coil is giving a restraint and your current coil is giving the forward torque. So that means we can say this simple impedance relay is an overcurrent relay with voltage restraint. This is another component is added in the overcurrent relay. Therefore it became the impedance relay. Okay. Now we'll see the implementation of the simple impedance relay using balanced beam structure. How we can implement this. So this is a black box simple impedance relay, and we'll have a setting of Z set, and when we'll feed the voltage and the current, that is voltage at relay point VR and the current at relay point IR, then accordingly it will give the trip command when your ZR is less than Z set, right? This will trip, and your ZR when it is greater than Z set, it will restrain, and when your ZR is equal to Z set, that is the verge of operation, that is the boundary point. Okay. So now we can see a balanced beam structure where we can easily see here that there is a balanced beam where both sides we can apply the torque. The spring is connected at one end, it provides a force here, right? And we have at the two end we have two coils. One is your operating coil and other one is your voltage coil, right? This is in fact the current coil, and or we can say the operating coil. This is your voltage coil, which is also called restraining coil, which produces the restraining torque, right? So now if we'll apply current here, that means it will give operating torque. So here when your operating torque will become greater than the restraining torque, okay, so at that point this contact will just short circuit this both the point, right? When it will short circuit, it will give a trip command to the circuit breaker. So this is how it operates. This is the balanced beam structure of operation, right? So as we have seen that voltage coil gives a restraining force and your current coil gives a operating force. So when your operating torque is greater than, or operating force is greater than the restraining force, so it in fact it will give a torque, right? Okay. So that way it will short circuit the two contacts, trip contacts, and it will give a trip signal to the circuit breaker. This is a very simple structure. So now let us see the performance of this impedance relay under different conditions. Okay, so under normal load condition, how it behaves. Under normal load condition, how it behaves. In fact, let us consider this. How the impedance relay performs during the normal load condition. Under normal load condition, we can see here the operating point lies here. Why it lies here in the fourth quadrant? Because generally we know that in the transmission line, because of the Ferranti effect, the line becomes capacitive because of the charging current, right? And therefore it gives little capacitive effect at the end. Okay, so whatever voltage or current will be read by the relay will have some capacitive current, right? Little capacitive current if your load is not very high. If your load becomes very high under heavy loading condition, your operating point may move towards this, right? Maybe move towards the first quadrant condition. But under normal load condition, your operating point lies here at this point, little capacitive, right? Okay, so therefore, so this is your line fault characteristic considering the arcing fault, right? Considering arcing fault, this is your fault characteristic, and this is your normal load, where under normal load condition it should lie in the restraining region, right? And also it is lying in the restraining region, right? So therefore it will not trip under normal load condition. Okay, so if some abnormal condition happens, it may come inside the impedance, inside the operating characteristic, and then the relay operates, right? Relay trips. Now we'll see the effect of arc resistance on the reach of the simple impedance relay. Already we talked about this, right? So because it already we talked about this, let us a little bit talk more about this. Now this, with this line, the arcing fault is happening here between bus A and bus B. Okay, now for this the reach is up to bus B, that is your Z set. Okay, up to bus B the setting point is given to the relay. Now for the arcing relay, if the arcing fault happens at point B, then your net impedance will be somewhere here, right? But as it is, the fault is happening at point C, it is exactly coming to here. That means your CR is your arcing resistance that is added to the impedance. So that will give us the net impedance here, right? Okay. So if the arcing impedance happens here at bus B, then your net impedance happens to be here. So that means it is lying outside the trip region. So that means it will restrain, right? So as we are considering the point at C, the fault point at C, therefore it is exactly at the verge of operation. So that means your relay is under reach by this distance or by BC, right? Okay. So therefore if we'll calculate the percentage under reach, this is restraint, percentage under reach, then how we'll find this? Your under reach, the relay is under reach by BC, and your actual reach is AB, which is set point, right? So therefore the percentage under reach for this arcing fault is BC by AB into 100. So BC is the distance of under reach by which the relay is under reach, and the actual setting is AB. So therefore the distance of under reach BC by the actual setting AB into 100. So that will give us the percentage under reach. So in fact this kind of relay is called, because we are considering the distance, right? Always when we are calculating the impedance, the distance is the major factor, the fault location, or the distance of the fault location from the relay point. So therefore it is known as the distance relay, right? We call it distance protection schemes. Okay. So then let us examine whether it has a directional property existing or not. So directional property exhibited by the simple impedance relay, whether it exhibits the directional property or not. Let us see it. So here we can see the set point, right? Here the relay is connected at bus A, and this feeder has bus C and bus B. There are 3 buses, right? And if your set point of the relay is Z set, now in this direction it will also act, right? And also in this direction it will act. So because in the reverse direction, whatever current will flow, whatever current, suppose the fault happens here, okay, then it will also measure the current and voltage fit, and it will compare with Z set. And if the fault happens here, again it will also measure, and though the current direction is in the reverse direction, both the current direction in the opposite direction, but still it will give a trip command if the Z value seen by the relay is within the Z set value, right, or a reach value. Now you can see the fault characteristic. The fault characteristic is a straight line passing through the origin, and this is your operating characteristic, right? And we can see here bus A is here, and for bus B the location is here, and for bus C the location is here, and the fault characteristic. Now if the fault happens at between A and C, your fault location will be somewhere here on the fault characteristic. And if your fault happens somewhere in between A and B, your location, that point, fault point, and the fault characteristic will lie somewhere here. So within A and B, this is within A and C. So therefore all these points are lying within the trip region. So therefore your relay will respond, or relay will trip, whether the fault happens in the AB or fault happens in the AC. That means irrespective of the direction of the fault current, so it operates. That means That means your impedance relay doesn't have the directional property. That means simple impedance relay, SIR, simple impedance relay doesn't have directional property, right? So that means it cannot be used for directional purpose, right? So therefore impedance relay is modified. Further we'll see it is modified to reactance relay and then more relay, right, which has the directional property. We'll see in the next class. Okay, so thank you very much. Thanks a lot for your kind attention. Thanks.